Today's video is going to be all about redox reactions. Redox reactions refer to reactions where reduction and oxidation is occurring in the reaction. This is going to be any reaction where we have electron transfer present. But what is oxidation and reduction? You'll be familiar with the acronym oil rig. This spells out for us that oxidation is loss, and reduction is gain. But loss and gain of what? Well, oxidation is loss of electrons or loss of hydrogen. Reduction is gain of electrons or gain of hydrogen. Oxidation can also refer to the gain of oxygen, as the name suggests, oxidation, and reduction, therefore, is the loss of oxygen. If we look at a simple equation like below, where we have sodium reacting with chlorine to give sodium and chlorine as ions, we can see, looking at the oxidation numbers, which of these species has been oxidized and which has been reduced. So if we assign oxidation numbers to start with, we see that sodium, being in the solid state, being uncombined, has an oxidation state of 0, as it's in its elemental state. Chlorine, being uncombined also, being in its elemental state as a gas, also has an oxidation state of 0. If we look at the products now, sodium has gone to sodium 1+, and now has an oxidation state of +1. Chlorine has gone to chlorine minus, or the chloride ion, and now has an oxidation state of -1. We can prove this by looking at the half equations. If we look at sodium losing an electron, so going to sodium plus an electron. Chlorine, on the other hand, is gaining an electron, going to chloride. If we combine our two equations together, we can cancel our electrons, as they are on opposite sides of our arrow, and so cancel out. We end up with sodium plus a half Cl2 going to Na plus Cl minus, just like our equation above. Now, from this then, we know that sodium is being oxidized as it's increasing the oxidation number from 0 to +1. Chlorine is being reduced as its oxidation number is going from 0 to -1. So what does this mean in terms of which is the oxidizing agent and which is the reducing agent? Well, an oxidizing agent accepts electrons itself being reduced. So which species has accepted electrons being reduced itself? Well, chlorine has, because it's accepted an electron going from Cl in the 0 oxidation state to Cl in the -1 oxidation state. And we can see from our half equation that it accepted 1 electron. So chlorine, or in our case, half a chlorine, is our oxidizing agent. Our reducing agent is the opposite. The reducing agent donates electrons, itself being oxidized. So if we look at which species has been oxidized, the sodium has gone from 0 oxidation state to +1 oxidation state, and in the process has lost an electron or has donated an electron to chlorine. So sodium has been oxidized itself, but has donated electrons, and so is the reducing agent. So in our example here, sodium is our reducing agent. So let's look through some rules to see how we can assign oxidation states. The first rule is that in uncombined elements, such as your noble gases like helium and argon, your oxidation state will always be 0. These elements have a full octet and they are fine just being by themselves, so they won't combine with anything, so they're always going to have an oxidation state of 0 as they won't partake in our redox reactions. The second rule is that uncombined elements such as O2 and H2 or Na as a solid. Basically, these elements are in their elemental state, and so they'll also have an oxidation state of 0. As we saw before with the Cl2 gas and the sodium solid, they had an oxidation state of 0, just like our elements do here. Oxidation numbers are easy to assign for monoatomic ions, such as sodium plus or iron 3+, as when they're by themselves, the oxidation number just equals the charge that's on the ion. So for sodium, it would be +1. For iron, it would be +3. When you have compound ions, the overall oxidation state is the ion charge. Just like here, the overall oxidation state was the ion charge, but they were by themselves, so it was easy to decipher. Combination ions, such as SO4 2-, have an overall oxidation state of the charge, so -2 in this case. Oxygen, being the more electronegative atom, would have a negative oxidation state, and sulfur would have a positive oxidation state. Because oxygen is in group 6, we would have a -2 charge if it was to form an ion. So the oxidation number of the oxygen equals -2. Now we have 4 oxygens, so we know that 4 times -2 will give us an overall oxidation contribution of -8. Now the sulfur has to balance this out to get to -2. So sulfur will have an oxidation state of +6, as +6 minus 8 gives us -2 overall. The same process can be done for neutral compounds. These are things such as Fe2O3. Now this has an overall oxidation state of 0, as there's no charge present. Now, just like before, oxygen, being the more electronegative atom and being in group 6, will give us a charge of -2 when it forms an ion. Because we have 3 oxygens, we're going to do 3 times -2, giving us -6. Now, because the overall charge is 0, the ions are going to be cancelling out the -6. So our Fe2 must give us +6. Because we have 2 ions, we know that we're going to get +3 overall if we just divide our charge by 2, because there's 2 ions present. This gives us an oxidation state of +3. So our ion, written in the Roman numeral form, would be iron 3. Now, there is some rules to help us always do this, some of which we've been using so far. The oxygen will always have a oxidation state of -2 when combined, apart from in a few special cases. So if oxygen is paired with a more electronegative atom, such as fluorine, then we get an oxidation state of plus instead of minus, because the fluorine will always have the oxidation state of -1, being in group 7 and being the most electronegative atom. So that means in this case, oxygen, as the overall charge is 0, must have an oxidation state of +1, as we have -1 for each of the fluorines, so -2 overall. Now we have an oxidation state of +2 to cancel that out, but as we have 2 oxygens, it's going to be +1 for each of them. So oxygen in this case would have an oxidation state of +1. We can also have an oxidation state where we have +2 if we have OF2. In the same way, fluorine will have an oxidation state of -1, giving -2 overall as there's 2 fluorines. And the oxygen will have to cancel that out as we have an overall charge of 0. So this will give an oxidation state on the oxygen of +2. And then obviously, as we said, oxygen in its elemental state will have an oxidation state of 0 instead of -2. Now, this is also the case in peroxides. So in water, oxygen, as we know, would have a -2 oxidation state, and the hydrogen would have +1 each, giving +2 overall, to give an overall charge of 0. However, in H2O2, the oxygen contributes -1 each, and the hydrogen contributes +1 each, also giving an overall charge of 0. These are just a few exceptions to the rules that we can always use to assign our oxidation states within compounds. Now, our combined hydrogen, as we've just seen with the water, will be +1. And this will be the case in most of our compounds that we see. The only time it will differ is if hydrogen is present in something like sodium hydride. So in this case, the hydrogen is actually more electronegative than the sodium, and so the hydrogen forms the negative oxidation state, and the sodium the positive. So sodium contributes +1, hydrogen contributes -1. So the hydrogen has a -1 oxidation state in this case, in order to give an overall charge of 0. All you need to do is remember that your group 1 elements will always give an oxidation state of +1, as they would like to lose an electron. So in this case, your hydrogen accepts the electron and is a hydride instead. So let's look at an example question. We've got magnesium burning in oxygen to form magnesium oxide. Now we can write half equations for this based off the reactants that we know we have, and we know what product we're going to form as well. So we know that magnesium is burning in oxygen, so the oxygen must be O2 gas. Now we know that O2 is going to form an oxide, so it's going to be O2-. We have 2 oxygens in our O2, so it must be forming 2 O2-. We know we need to add 4 electrons to give this oxygen enough electrons to form the O2-. Oxygen is in group 6, so has 6 outer electrons. It needs 2 more each to form the 2- and get its full octet. The magnesium, being in group 2, is going to form a 2+ ion. So we know it's going to be Mg2+. Because it's formed the 2+ from the 0, as this magnesium was in its elemental state and so had an oxidation state of 0, we know it's going to give out 2 electrons. Now we have our half equations, all we need to do is balance out our electrons. So we see here that the oxygen, we need 4 electrons, but our magnesium only gives 2 electrons when it reacts. So we must have to times the magnesium by 2. So we must have 2 Mg going to 2 Mg2+ plus 4 electrons. Now everything balances out. We can write our reactants on one side and our products on the other. So we can have O2 plus 4 electrons plus 2 Mg goes to 2 O2- plus 2 Mg2+ plus 4 electrons. Now we can cancel out these electrons on both sides as they're on both sides of the arrow. So we're left with 2 Mg plus O2 going to 2 Mg O. You can see here that our charges balance out 2- and 2+, so they must be in a 1-to-1 ratio. So here we have MgO. Now we have 2 of each, so we must have 2 MgO as our product. In the next example, we have aluminium reacting with chlorine to form aluminium chloride. Now the aluminium, being in group 3, is going to form a 3+ ion. So we get aluminium 3+ plus 3 electrons. The chlorine, being in group 7, is going to form our chloride ion. So we know we're going to end up with Cl-. Now we have 2 chlorines, so we must have 2 Cl-. Now, in order to get to the 2 Cl-, we have to supply 2 electrons to this. So these are our half equations. Our chlorine is being reduced from 0 to -1. Our aluminium is being oxidized from 0 to +3. Our electrons don't balance out, just like the previous question. So we have to find the lowest common multiple of the two in order to balance out our electrons and therefore balance our equation. So as you can see, the lowest common multiple of 3 and 2 would be 6. So we have to times our aluminium equation by 2 and times our chlorine equation by 3. This will give us 2Al going to 2Al3+ plus 6 electrons. We will then have 3Cl2 plus 6 electrons going to 6Cl-. So now you can see that our electrons balance out. All we need to do now is combine our reactants, combine our products, and cancel out our electrons to get our overall equation. So we have 2Al plus 3Cl2 plus 6 electrons going to 2Al3+ plus 6Cl- plus 6 electrons. Now you can see that we can cancel out our electrons again, and we're left with our ions to balance out. So you can see that our aluminium has a 3+ charge, each chloride has a minus charge, so we must have 3 chlorides to go with each aluminium. So we can rewrite out our overall equation up here with the electrons cancelled out to give us 2Al plus 3Cl2 going to 2Al Cl3. So you can see that our charges balance out. Our aluminium would have a 3+ oxidation state. Our chlorines would each have 1- going to -3 overall. So this balances out. It may not always be obvious what's going on. Our previous examples were quite simple. All we had to do was balance our electrons. But now we're given a case where it's not just balancing electrons. We're going to see how we add water and add H+ ions to help balance things out before we can then balance our electrons. So we have acidified manganate 7+ ions in MnO4- being reduced to Mn2+ by Fe2+ ions. So we know that if iron is reducing the Mn2+, it must itself be being oxidized. We know that iron can be oxidized to the 3+ oxidation state, giving away an electron. Next, we come on to our manganate. We have MnO4-, as it's told us in the question, and we know that we're producing Mn2+. Now, this isn't as simple as it seems because our oxygen isn't accounted for on the right-hand side, and we know we have to balance things as the oxygen can't just disappear. So we have 4 oxygens on our left-hand side. So to balance that out, we add 4 waters to the right-hand side, as our oxygens now cancel out. But in doing so, we've added ourselves another problem. We now have 8 hydrogens that we can't account for on the left-hand side. So this is where we add H+ ions in order to cancel that out. So we add 8 H+ ions. We know the reaction is going to be in solution, so they must be H+ ions that are reacting here. The next step is to balance our charge. As you can see, we've now added more charge to the left-hand side than is on the right-hand side. we have a minus and 8 pluses, but on the right-hand side, we only have 2 plus. So we have 7 plus against 2 plus. So this means we need to add 5 electrons to the left-hand side in order to cancel out our charge. So if we add our 5 electrons, go into Mn2 plus 4H2O, we can see that we're now fully balanced here and our half equation makes sense. Now all we need to do is balance our electrons from this half equation and this half equation. This is our reduction half equation. This is our oxidation half equation. So you can see that we have 5 electrons in our reduction and we only have 1 electron in our oxidation. So if we times this by 5, that will get them to cancel out. And we'll now have 5 Fe2 plus going to 5 Fe3 plus 5 electrons. So our electrons now cancel out, and this makes sense. All we have to do is write our reactants and our products on the same side as we did before, cancel out anything we can, then we'll have our overall equation. So if we have MnO4 minus plus 8H plus 5 electrons plus 5 Fe2 plus going to Mn2 plus 4H2O plus 5 Fe3 plus 5 electrons. Now, just like before, we can cancel out our electrons as these are on both sides of our arrow. So we are left with MnO4 minus plus 8H plus 5 Fe2 plus going to Mn2 plus 4H2O plus 5 Fe3 plus. So everything's now balanced out and we have our overall redox equation. So here we have a similar example where we have our iron 2 plus reducing the chromate 6 plus, which is Cr2O72 minus ion, to chromium 3 plus. So we know that our iron 2 plus is going to be our reducing agent, just like before. So it's itself going to be oxidized. So we see it be oxidized in the same way, where it gives up an electron, forming the iron 3 plus an electron. That's all the same. But now it's not clear what's going on with our chromate. So we can see that we have our chromate going to chromium 3 plus. Now, because we have 2 chromiums on the left-hand side, we need to balance that out with 2 chromiums on the right-hand side as well. But you can see that our oxygen doesn't balance out like before. We have no oxygens on the right-hand side and 7 oxygens on the left-hand side. So we need to put in 7 water molecules in order to balance that out. But now we've made the same problem where we now don't have enough hydrogens on the left-hand side to balance out with the hydrogens on the right-hand side. So we need to add in 14 H plus ions in order to balance that out. But now you can see that our charge doesn't balance out. We have 2 minus and 14 plus on the left-hand side, giving us an overall 12 plus. On the right-hand side, we only have 2 3 pluses, giving us a total of 6 plus. So in order to balance this out, we need to bring down the left-hand side by 6. So to do that, we add 6 electrons. So we say plus 14 H plus 6 electrons going to 2 Cr3 plus 7 water molecules. Now we have a complete reduction half equation. So we have our oxidation half equation, we have our reduction half equation. Now all we need to do is balance out our electrons between the two. So you see that in order to have enough electrons from the ion, we're going to have to times this equation by 6. So that will give us 6 Fe2 plus going to 6 Fe3 plus 6 electrons. So if we write out our reactants and products all in one equation, then we will have our chromate ion plus the 14H plus the 6 electrons plus the 6 iron 2 plus go into 6 iron 3 plus 6 electrons plus 2 chromium 3 plus 7 water molecules. So we can cancel out our electrons just like we have been doing. And now all we need to do is just rewrite this out as our finished overall equation for the redox. H plus 6 iron 2 plus 6 iron 3 plus, going to 6 iron 3 plus 2 chromium 3 plus 7 H2O. And this is our finished overall redox equation. You might see some special cases where we have a disproportionation reaction. Now this seems like a mouthful, but it's quite easy to understand. This just means that in our reaction, we're both oxidizing and reducing the same species in the same reaction. We can see this with our peroxide decomposition. So this is going to go to 2H2O plus O2. So if we look at our oxidation states within these molecules, we see that we have +1 for each of the hydrogens, giving +2 overall, but it has an overall oxidation state of 0. So that means that the oxygen must be -1 each. Remember, this was one of the special cases where we see that oxygen isn't 2- in a combined state. So here we go to the water where we have +1 for each of our hydrogens again. We have 2, so it's +2 overall. So our oxygen here must be 2-. Here we have uncombined oxygen, or oxygen in its elemental state. So this means that it's going to have an oxidation state of 0. So we can see that we've started with oxygen only in the -1 oxidation state. We've gone to the -2 oxidation state in water and the 0 oxidation state in oxygen gas. So as you can see, we've both reduced and oxidized our oxygen here. So as we can see, we've both reduced the oxygen from -1 in the peroxide to -2 in the water, and also oxidized the oxygen from -1 in the peroxide to 0 in the oxygen. This is why we have both reduction and oxidation happening at the same time. So this is what we call a disproportionation reaction.